Good, that's screen number 3. Let's go take a look at the syllabus. I posted a new version of the syllabus. That's going to be version number 4. The only thing that was missing in the previous version was the course objectives. Okay, so I managed to find it and pasted that into the document that's now there on Canvas. Okay, that was the only thing that was missing from the syllabus. We have summary of links, okay, and so on. Now, where are we in the schedule? We are right in here, in the schedule of classes 1D motion, which already started covering last time. Okay, go. So we started with the definition. The primary definition was position, and then I told you about the displacement. I called that a secondary definition, and everything else that follows from that is going to have a higher order definition, right? Tertiary, quaternary, and so on, right? And I want you to pay special attention here to the definition of instantaneous velocity. Average velocity is defined like you saw before, right? Delta x over delta t. Let's go back here. Here you go. Delta x over delta t. Instantaneous velocity is a velocity at very instant. At the very instant means what? That delta t is equal to 0. Okay? But if delta t is equal to 0, delta x must be equal to 0 too. And we get this funny number, which is 0 divided by 0. Okay? But 0 divided by 0 is not necessarily 0 nor infinity. It can be a finite number. Okay? And I gave you an example for the case of a ratio of sine of x divided by x. Remember that? Here you go. Sine of x divided by x has a finite value. And I did that for you in the last class, right? Using, let's take a look here. Not this one right in here. Remember we did that, let's see, right in here. Sine of x, okay? Freeze panes, we go. I calculate, I have x here, I have sine of x here, and I divided sine of x divided by x. As x goes to 0, to a very small number, notice that the ratio between sine of x to x goes towards 1, okay? So at x equal to 0, it's very reasonable to state that this ratio that you see right here is going to be 1. So remember, and by the same token that we have something like that for the sine of x divided by x, we have something else like that for the limit of delta x over delta t. Okay, it's going to be a finite number when we calculate that. Okay, in practice, when in real life, when we are measuring delta x over delta t, okay, we do not measure delta x for a finite, for delta x equal to 0 and delta t equal to 0. We don't do that in practice, in real life. But we do that for a very small delta t. That's what your speedometer is all about. Your speedometer measures the distance that your car displaces in a very small amount of time. They usually get the full rotation of your tire to find out your so-called instantaneous velocity, okay? And this delta t is going to be very small compared to the amount of time that you are being subjected to, or even the distance that you are displacing. So let's say 10 meters, right? You displace 10 meters. The circumference of your tire is going to be much less than 10 meters. So your measurement of the instantaneous velocity is going to be very close to the actual value. Okay, and remember that there are all sorts of different there are different types of velocities, instantaneous velocity, that I'm going to cover with you. So let me just spell that out for you. Page. Today is September 11, 2023. Okay. We call the definition of instantaneous velocity, right? The instantaneous velocity is abbreviated by the letter V to make a distinction between average velocity, right? Average velocity is V and subscript AVG. Okay. Just going to repeat what I told you right now. It's always good to write that down, what we say, so you can remember it more easily. Okay. When we have a situation in which, two parameters, one parameter in which one parameter divide another one, and both parameters are set to approach 0. Under certain, let's see, under certain situations, let's see, let's put it this way, under certain situations, right, in which one parameter divide another one and both parameters are set to approach 0, we may have a finite number, just like we saw for sine of x divided by x whenever x goes to 0. Okay? In the case of the instantaneous velocity, we also have a similar situation. However, in practice, okay, in real life, right? In real life, we cannot measure the displacement for a delta E equal to 0, right? Equal to 0. So what we do, in the case of instantaneous velocity, right? So what we do, we measure the delta x for a very small amount of time. For instance, in the case of your car, the delta t is measured for a full rotation of your wheel. Okay? Of your tire, let's put the full rotation of your tire. Okay? Which ends up being very small if compared with the displacement we usually have with a car, say tenths of kilometers. Okay. That's what we do in practice. We get a very small amount of time, and within this amount of time, we measure the displacement of the car. And the displacement is usually a full rotation of the tire of your car. So there is a device that counts how many rotations your tire underwent. And there is also another device that measures how long it takes for a single rotation of the tire, okay? That's how we do it in practice, in real life. Notes. Furthermore, here I'm giving you just a qualitative here. I am giving you just a qualitative idea of the instantaneous velocity, okay? To really understand it, of instantaneous velocity. To really understand it, we must use calculus, okay? But we don't do that here because this course is not a calculus-based physics. However, we don't do that here because this is not a calculus-based course. Okay. But there's another way. There's another way. There is another way of finding out the instantaneous velocity. And how do we do that? This other way you must know, okay? This way involves the plotting of the x position along the vertical axis and versus the instant of time t along the horizontal axis. Okay, so let's take a look here. I'm going to show that to you. Let's take a look at this. Yeah, here's the slides that we're looking at, right? Illustrating the displacement, right? Average velocity as well. We did that before. And here you go. Here we have a plot of two positions of our object, okay? So here you go. Notice, let's see. Notice that initially at time t equal to 0, the object that I'm considering is at position 4 centimeters, okay? Just like I showed to you before here in this other illustration. Here is one way of illustration the position of the object. Here is another way of illustration the position of the same object, okay? In this case here, we have the x-axis showing the initial position of the object, including its instant of time, and the final position of the object, including its final instant of time. Here we have a different way of plotting the position of an object in terms of an x versus t graph. At time t equal to 0, the position of object is 4. At time t equal to 3 seconds, the position of the object is 7 centimeters, okay? For the case of the average velocity, what's going to be the average velocity? When you plot something like that, the average velocity is going to be the slope of this line that you see right here. Is the rise divided by the run, right? The rise is delta x, 3 centimeters, and the run is going to be delta y, right? Delta x for this one. And the run will be delta t, which is also the same number, but with a different unit, 3 seconds. So the average velocity in this specific case is illustrated as being the slope of this line connecting those 2 points, okay? So let's write it down. Okay. There's another way of finding out both the...
Professor, I'm
yeah.
sorry to interrupt you, but what did you say? Like losing points?
Let's see. Are you talking about the graph here?
Yeah, but you said something about losing points, so I couldn't really understand what you said.
Well, here you go. Let me just repeat what I said, right? So there are two ways. There's another way of determining the average velocity and the instantaneous velocity, right? That's what I was going to repeat. That's what I was going to correct here. There's another way of determining, right? Determining the average velocity and average and instantaneous velocity. Okay, it's another way, and this way involves plotting, right? The x position along the vertical axis versus the instant of time t along the horizontal axis. So let's look at the average velocity first. Let us look at the average velocity first, right? And going back here you go. So I'm giving you an example. In the case we illustrate last time, right? Comma. The initial position, right? The initial position of the object, right, was 4 centimeters. The initial position, and I'm going to put here at t equal to 0. Position of the object at t equal to 0 was 4 centimeters, and the final position, and its final position, right? Its final position at t equal to 3, at t equal to 3 seconds, was 7 centimeters. Okay. What do we do? We plot x versus...
Professor, right? I'm sorry to interrupt you.
Yeah.
So you didn't say anything about losing points or anything like that?
I don't understand what you're saying. Can you type for me in the chat box? You said losing point. I don't quite understand. If you can type it.
I thought. Okay.
If you can type it, I will understand better your question. Okay. So. Okay, so we plot x versus t, right? On a graph. We plot these 2 points, right? These 2 points. And these 2 points will be what? 0 and 4 centimeters. And 3 seconds, 7 centimeters. These 2 points. On a graph x versus t, okay? So let's look at the average in the case we illustrate last time, right? 1, here you go. We plot these 2 points on a graph x versus t. Then we connect these 2 points with a straight line. Straight line. And 2, 3. Finally, we measure the slope of this straight line. Okay. Finally, we measure the slope of this straight line. That's another technique that we use to find out not just the average velocity, but also the instantaneous velocity. Okay, a graphical way. So going back here you go. That's my line, the slope of this line, which is going to be delta x over delta t, is going to coincide with the average velocity. The slope of this line coincides with the average velocity. Okay, we do something similar. We do something similar to the instantaneous velocity. The difference being that in this case, we have an infinite amount of points, right? Amount of points in the graph, right? For the average velocity, we have a finite amount of points in the graph, but for instantaneous velocity, we must have an infinite amount of points. Here you go. Here you go. Here is an example of a particle that's moving in the x-plane, right? Position of the particles changes as time goes by. Let's say the position of the particle, is represented by this genetic line, right? Okay, and I come to you and say, look, first, that's how the position of the particle varies. Suppose that I study very carefully this particle, this motion of this particle, and I can plot this very detailed graph of the particle. Okay, what did I mean that I have a finite amount of points? I have a finite amount of points because we have several points in between. What this graph is implying is that you have several points along this line, and those points are very close to each other. Okay, I'm not illustrating every point here along this line, but what this line is telling us that you have several measurement points along this line, and the delta t between them is very small, even going to zero. So we can even state that we have infinite amount of points here. Okay. So if we want, you already know how to find out the average velocity of a particle, right? Between, let's say, T1 and T2, that we already know. So all we have to do is connect a straight line between those 2 points and measure the slope, right? But we're not talking about the average velocity. Now we are talking about the instantaneous velocity. So let's go there. What do you do to find the instantaneous velocity? We do exactly what I told you to do, right? We have to make delta t, t2 minus t1 becomes infinitely small, okay? So let's see here. I'm gonna do it in a better way. Let's see. It's gonna be done like that. Here you go. If I want, for instance, to find out the instantaneous velocity at t2, right? What do I do? I make t1 as close as I can to t2. Okay, and how is that done? Here you go. Approach t1 as close as you can to t2, right? Delta t here is becoming small, right? T1. And here you go, T2. See, we have a different slope right now. And then we're gonna get my T1 closer and closer to T2. That's the mathematical procedure, okay? And that's a very time-consuming procedure, by the way. Very soon I'm gonna tell you what's the easiest way of doing it. You approach T1 to T2, right? Here, the slope of this straight line is going to be the average velocity between those 2 points. If you want to know the instantaneous velocity between those two, at t equal to t2, what do you have to do? You have to make those 2 points so close to each other, very close to each other, to the point where the delta t is going to be 0. You're not going to do something like that in the exam, okay? In the exam, you're going to do something else. You will have to memorize that the instantaneous velocity for a graph like that is going to be what? Is going to be the slope at the point T2. Okay? So as I approach T1 to T2, this straight line here approaches the slope. Is going to approach a slope. There's going to be a special type of slope. It's going to be the slope of a tangent to that point in there where T2 is located. I'm going to take T2 coincides with T1 like that. Okay. Then like that. T1 approaches T2. When T1 approaches T2, okay, the instantaneous velocity is going to be given by the tangent, the line tangent to this point in the curve. Tangent to this point. Okay? Is the average velocity. When is the average velocity? Now, when when T1 approaches T2, approaches T2, comma, the instantaneous velocity is represented by the slope of the line tangent to the curve at T2. Okay? That's what you have to know. And I'm going to write that down there. Let's see if I need that. Yeah, here you go. I have a better illustration here. Right? I can. Here you go. In a v versus, in a x versus t, here you go. X, in a x versus t graph is the instantaneous velocity. Here I'm illustrating the tangent. I don't think I need the other ones. Yeah, I don't need that. I need the other. Let's erase that stuff. Delete slides. And I'm going to you say anything about losing points? No, I don't remember saying that. Maybe I have misspoken. Okay, Camden. Okay. Okay, so let's document that in my notes. In the graph, okay? So we do the following. One, One, initially, right? Initially, we must have a graph of x versus t. This must be given. This must be given. This must be given. Okay. Two, suppose you wanted to know the instantaneous velocity at t2. T2. Okay. You get 2 points on the graph. One at T2 and the other one at any point along the curve. I call this point any point along the curve at, say, T1. T1.
Professor, I have a question.
Yeah.
Are you going to share the PowerPoint file as well?
Yeah, the PowerPoint is a little bit more difficult to share, okay? So
okay.
you will need to follow it through the video. Okay?
Oh, okay. Video. Okay.
Okay.
Thank you.
Okay, welcome. One at T2 and the other at any other point along the curve, say at T1. Okay. Then you connect these 2 points with a straight line and find the slope, right? In the next step, you approach T1. You approach T1 to T2. To T2. And repeat. In the next step, you approach T1 to T2 multiple times, right? You make, let's say you approach, you make, in the next step, you make T1 closer, right? To T2 multiple times. And repeat step 4. Step 4. Eventually, when T1 is equal to T2, T1 is equal to T2, comma, you realize that the previous slopes approach the slope of the tangent at point T2. Okay, so that's how you find out. That's another way of finding out the instantaneous velocity. Okay, so in conclusion, the instantaneous velocity is given by the slope of the tangent at the point in the curve. Okay. Okay, go. You want to know the instantaneous velocity at this point here? You take the slope there at this point. You want to know the instantaneous velocity at this point here? Okay, what do? You find the slope of the tangent at this other point, right? And so on. I'm going to do the following. I'm going to take out this point here. So it makes easier for me to figure out what's the, the tangent right in here. Here I'm just eyeballing, but there is a mathematical procedure to do that, okay? Like that. The instantaneous velocity at this point is the slope of the tangent at this point, and so on. Okay? So okay. The instantaneous velocity, here you go. At any point along a curve, at x versus t, along the x versus t curve, is the slope of the tangent. The slope of its tangent. Okay? That's what we have to remember. For average velocity, the average velocity is the slope of that line that connects 2 points in the curve, in the x versus t graph. For the instantaneous velocity, is going to be the slope of the tangent at a given point along the curve. Okay? That's what you have to know. And here in this course, we are going to, in this course, we are going to study different types of motion, okay?
Professor, I have a question. So
Yeah.
T2 is always going to be the tangent point, like it's never going to be interrupted by any like line or anything. Just
Well, I guess you meant if this curve here is going to be continuous. Is that what you meant?
yeah, and then tangent lines, and the tangent lines never going to touch the other line, right?
No, it may touch. It may touch. Depend on the point where you're taking the tangent. Okay. Let me see. Let me give you an example. Let's see. Right here. Let's see here. Let's see. It is possible. Let me give you an example.
But if it's possible, is it going to penetrate, or is just going to remain as tangent point again?
Let me give you another example. Hang in there. So I hopefully I'll be able to answer your question. Here you go. There are some examples out there. Here you go. Let's try this one here. Yeah.
Okay.
This one like that. Let's see here. You mean whether the tangent line is going to intersect another point? Is that what you mean, right?
Yeah.
It's possible that that we intersect another point in the curve. Yeah, it's possible. But let's see. Let me see. Let me give a nice example here. I'm gonna do that. Maybe this way. Yeah, this way. Suppose that we have a curve like that, right?
Mm-hmm.
Suppose that we have a curve like that. Let's see. Let's see here. Uh, uh, let's see this one. Yeah, let's say here. This tangent, yeah, that's right, you're right. Okay, the tangent will not intercept the oh, let's see, it may, depending, let's see where you get that. See here, in this case, right? In this case here,
Okay.
in this case here, if I'm taking the tangent at this point, it is intersecting the line, okay? So it's possible, yes, it is possible that you're going to intersect the line. Like here, let's see, at this point here, see that? I'm taking the tangent here at this point, so it is possible that you are going to intersect the line elsewhere, right? You're taking the instantaneous velocity at this point here, and the tangent at that point can intersect the curve elsewhere. Yeah, it's possible. Okay.
Oh, okay.
Okay. That's the answer to your question, right?
Yes. Thank you so much.
It all depends on the curve that we're dealing with. Okay. And that's what 9:54 right now. Let's see, 9:35 right now. Let me show you something else too. Okay, let's see here. Before we move forward, I want to show you something in the canvas. Canvas site. Oops. Okay, so here you go. I put the notes here that we are working on fall 2023. Okay. Here are the lecture notes for last year's course. Here are the lab notes for last year's course, okay? So now, if you want to know what we covered so far, look at these notes here. If you want to get ahead of the course, consult the notes of last year. And on the top of that, hey, I didn't publish that yet, huh? Okay, now we're gonna publish it. Good. I also post the link to the videos of the previous two classes, right? Here you go, is the class for 30 of August, which is the lab, and another lab, 6th of September, okay? So all you gotta do is to click here. If you want to watch again the lecture, right? That's gonna happen in the future, you can go to my YouTube channel. YouTube here. YouTube, let's see here. Here you go. My channel. Right? And then there's this playlist. Physics 6. Oops, I don't want to stop it here. Now take a look at the dates, right? The dates that we have. Okay, that's 7th of September 2022. And the two videos that I posted are here at the bottom. The material that I cover in those videos, right, is similar to the material that I covered last year. Okay, so that's what's new in the Canvas website. Confidence level table right here, and what's new here? Let's see. Oh, the syllabus, right? Version 4. These notes for 2023, and the links to the videos. So as we move along the semester, I'm going to keep on adding links for the other class meetings that we have, okay?
Okay. Professor, I have a question.
Yeah.
So, what do we need to study for the upcoming exam?
Yeah.
Like, do we need to study from textbook or from your lecture?
Everything, okay? So it's for the exam. Let me write that down here for you. For the exam. First, better one, do the homework, right? The homework. Do the examples in the class. and in the book. Okay. Read the notes. Okay, this is the minimum, the bare, the bare activity the bare thing that you gotta do, the minimum, that you have to do for the exams, right? And then if you have time, do more problems outside the homework and the examples. That's how I used to do when I was a student, right? I will do the exams. I will do the examples. I will do the problems in the homework. I'll read the notes. And then if I had time, additional time, I'll look for more problems, for more examples outside those two here. Okay. And by the way, the exams in general, exams are a mixture of multiple choice questions and numerical, multiple choice and numerical questions. Okay.
Okay, thank you.
That's what you should expect for the exam. And let's take a look at the book too. Let's see, Wiley Plus.
So it's going to be chapter 1 to
Oh,
2,
yeah, good
right?
question.
Or
Good question. Let's take a look here. Exam 1, right? It's going to depend how much material we cover, okay? So you should expect chapters 1 and 2 plus the lab 1 that we're going to do. That we're going to do on Wednesday. Okay.
So are we going to do the lab as an exam, or do we need to just like turn it in the lab homework?
Okay, the lab is let's see, the lab is scheduled for 2 class meetings. The first lab is scheduled for 2 class meetings. Okay. At the beginning, I usually do the lab twice because you're all unfamiliar how I do things, right? So you can see that we might have 2 meetings for lab 1. Okay.
Okay.
And then what happens? I take some questions from the lab 1 and put in the exams. So
okay, so we just need to submit it, right? We just need to submit the previous work, which is like.
Okay, when we do the lab, and I'm gonna cover that on Wednesday. Okay, when you do the lab, you have to turn in a lab report.
Oh, okay.
And we have to turn in a lab report. And in addition to that, right? So I have to put here, I forgot to add here to my notes. It's not just the homework. Read the notes, right? Get familiar with the lab, right? Because there will be some questions of the lab in the exam. For the exam, get familiar with the lab. There will be some questions. There will be some questions related to the lab on the exams. Okay. So that's the bare minimum that you have to, those 4 items here.
Are we allowed to retake the exam later?
I don't know. I don't do that, but
Okay.
it's an open notes, open book. Okay. The exam is open notes, open book. The exam and is open. The exams, right, are open note, open book. Notes, open book. Okay, and don't forget that there are 3 partial. There are 3 partial exams. 3 partial exams. Okay, and I dropped the lowest grade from the calculation, right? Of the when I calculate the final grade. Let's see. There are 3 partial exams, and I dropped the lowest grade of these 3 partial exams in the calculation of the final grade. In the calculation of the final grades. Final grades, right? So here you go. Material for the exams. Material for the exams. How to study for the exam, right? How to study for the exams. Do the homework. Do the examples in the class. Here you go. Do the examples in the book. Read the notes, get familiar with the lab, right? And if you have more time, okay, do more problems outside the homework and the examples. Wait a minute. Exams are a mixture of multiple choice and numerical questions. Okay. What I want to do, I want to take attendance. Lecture, not this one. Or, yeah, no, that's the one. Today is 11. Sky, Arbahal.
Here.
Okay. Next, Tessa, are you there?
I'm here.
Okay, thank you. Destiny. I see Destiny here in my list.
Yes, I'm here. Sorry.
Good, thank you. Gael Garcia. I see Gael here. Let's see if he's. Okay, good. Thank you, Gael. Eleodoro. Are you there, Eleodoro? I don't see Eleodoro here. Next is Ridwan.
Here.
Thank you. Ashley Izumo. I don't see Ashley. Okay, good. Thank you, Ashley. Norberto Lopes.
Here.
Thank you. Anabel Madrigal. I see Annabelle in my list. Are you there, Annabelle? Okay, I'm gonna put a star here in her name. Eric Martinez.
Here.
Thank you. Next is Vanessa Mena.
Here.
Thank you, Vanessa. Nazmoon Miller. I don't see Nazmoon. And next is going to be Catherine Pacheco.
I'm here.
Thank you, Catherine. Camden Park.
Yes, I'm here.
Thank you. Next is Victoria Preciado. I think I saw Victoria here today. I don't see her in my list. Preciado. Okay, next is Alexis. I don't see Alexis. Marcos Sanchez. Okay, so let's see how many students we have. 11, 12. Let's see, who is not called? Let's see, we have one more student here. Let's see here. Eleodoro is not. Annabelle Madrigal. Annabelle, are you there? Okay, and 12. Okay. Was everybody called, by the way? Let's see if the problem here. Ah, okay, the problem is here. Good. Now I have the right number. The problem was in my counting here. 9:49 right now. Let's take a break. Break from 9:50 a.m. to 10:05 a.m. Okay? So I'll see you in 15 minutes. Okay, I'm back here. And let's go back to our definitions we have so far, right? I didn't mention something. Those are definitions that we have covered so far. Okay, in addition to displacement, there is another important definition that I didn't mention to you. It's called distance traveled. Okay, and there is also this other definition that I didn't tell you. It's called speed. Okay, average speed, let's put it this way. Average speed. And instantaneous speed. Instantaneous speed. There is a very important difference between, let's start with distance traveled first. Okay, let's start with distance traveled. I'm going to give you an example. Here we go. So here we have this particle, and I'm going to copy and paste elsewhere. Right here. Right? So here we have this particle that moves from position 7 to position 4. Okay, and then back from 4 to position 7. That's the best way of understanding the difference. Okay, there you go. Consider this case, and I'm not going to call, let's see, I'm going to call it, I'm not going to call XF, I'm going to call X1, okay? A time t equal to 0. And then from X1 to this position, goes back to its initial position. Now I'm calling it XF, okay? According to the specific definition of displacement, okay, and I'm going to erase this thing here. And I'm going to even do the following, do better than that. I'm going to put everything in a single graph, in a single slide. Like that. Uh-oh. Okay, I didn't get mine. Like that. Move a little bit up. Oh. Okay. Like that. So the particle is initially here at this point, 7 centimeters, moved to the left position, and now I'm calling X1. Okay. here I'm going to write delta x is x1 minus x naught, and call that and then this is going to be at delta x prime because it's a different displacement. Okay, x final minus x1, right? Note see that x final coincide with x naught. Right? Note see that they are exactly the same, right? And let's see, here is going to be t equal to 0. This one is going to be t equal to 0. I'll call this one here t1. Right? I'll call this one t1 as well. Immediately after arriving at x1, he moves backwards. And that should be lowercase x. Why am I doing that? Well, I'm doing that to distinguish displacement from distance traveled. X naught. Okay. According to this, to the very definition of displacement, that's going to be my initial position. That's going to be my final position, right? According to the very definition of displacement, the delta x, the displacement in this case is going to be 0, because xf coincides with x naught. Make sense? Okay, so let's write it down. Distance traveled. Okay. Oh, Go. Consider the following case. Okay. 1. At t equal to 0, a particle is initially at position x naught equal to 7 centimeters. Okay. It then moves to x1 at t equal to t1. It moves from x naught 7 centimeters to x1 4 centimeters. Okay. At t equal to t1, it is not it move it. It is at x. Yeah, it moves. Let's put it this way. That's not right, huh? At t, it then moves. Let's put it then moves from x equal to 7 centimeters to x1 equal, and then I'm gonna put between parentheses that he's at x1 equal to 4 centimeters at t equal to t1. Okay. Finally, it moves back from x1 equal to 4 centimeters to x final, which by the way is equal to x naught, right? Equal to x naught at t equal to final, the final. Right? From, here you go, the strict definition of displacement. Okay. We have the following. We have the following. Yeah. Here you go. Delta x is equal to f x final minus x initial, right? But x final is equal to x initial. Consequently, the displacement is going to be 0. Okay. In this specific case, yeah, the displacement is 0 because of the very definition of the displacement. X final position minus initial position. Because the final position coincides with the initial position, the displacement must be 0. Okay, but the same does not apply to distance traveled. Okay, in the case of distance traveled, in this case, the distance traveled is going to be, in this case, distance traveled d. Okay, in this case, d is going to be what? D is going to be 7 to 4, which is 3 centimeters, plus 4 to 7, 3 centimeters as well. See the difference between distance traveled and displacement? Distance traveled is always a positive quantity. Okay? It's always a positive quantity. I want you to keep that in mind. Okay? And we need this definition of distance traveled because we're going to define as well speed. Okay. For the case of speed, for the case of average of speed, okay, we have the following definition. Speed we usually represent by the letter S, okay, is going to be distance traveled divided by delta t, like that. Okay, and by the way, we do not have this thing called average speed. We have just this thing called speed. Okay, I'm not going to define. We'll just talk about the speed only. See the difference now? In general, D is going to be greater or equal than delta x. Not in general. Well, we always have the following. We always have the following. D greater than delta x, okay? Greater or equal than delta x. D is always greater than 0. Always greater or equal than 0. And delta x, by the way, can be greater than minus infinity and less or equal, let's see, plus infinity shouldn't be equal, right? Or even better, if you want to put in the from the left to right, huh? Okay, keep that in mind. Okay, whatever you see in the odometer of your car, whatever you see in the odometer of your car, okay, is the distance traveled. Similarly, what the speedometer of your car indicates is the speed, not the velocity. Not the velocity. Okay? Not the velocity. Think about that. Okay, and let's take a look at the book now. That's what we have here in the book. Chapter 1, chapter 2, kinematics, one dimension. Displacement is speed and velocity. Okay, I didn't cover acceleration yet. We're going to cover acceleration now. But before we start covering acceleration, let me tell you the types of motion that we study in physics. Okay, in physics, in this course, okay, in this course, we will study the following types of motion. One, uniform motion. What means uniform motion? Constant velocity. Okay, uniform motion. And then accelerated motion. That's going to be constant acceleration, which is something I'm going to define what acceleration is. In this case, the velocity changes linearly in time with time. Okay. And then we have other types of motion as well. We have uniform circular motion. Okay. Constant, not constant acceleration. Yeah, it is constant. Let's see, it's constant speed. Okay. Uniform circular motion is constant speed. We can say also that the magnitude of the acceleration is also constant. And by the way, in this specific case, the speed coincides with the magnitude of the velocity. I'm going to put that in this case, the speed coincides with the magnitude of the velocity, but it's constant. Another type of motion that you are going to see in physics 39, not this course, okay, is going to be vibration. Simple harmonic motion. We call that simple harmonic motion. Okay? Sort of similar to uniform to UCM, which is uniform circular motion. UCM. CM. Sort. I'm gonna put a sort similar to. Sort of like that. I don't like that. But before we get into this type of motion, let's go ahead and define what acceleration is. And here you go. Let's take a look in the book. Displacement. Go displacement, okay. Delta x, see that? Delta x here. Speed and velocity, distance over elapsed time, that the average speed is. Average velocity, we covered as well. The notation is different because this guy already is talking in terms of vectors, okay? I don't like the way he does. You know, I leave vectors for the next step before we cover vectors, after we cover vectors. And example. We can come up with an example. Andy Green in the car, Trust SSC, set a record of 341 meters per second. This is supersonic speed, okay? Actually, transonic speed. We don't call it supersonic, we call it transonic. The car, it was 1997. The car was powered by two jet engines, and it was the first one officially to exceed the speed of sound. To establish such a record, the driver makes two runs through the course. This guy went to the desert to do this thing. Okay, it was right here in the California desert. To establish such a record, the driver makes two runs through the course, one in each direction to nullify wind effects. Yeah, okay. Figure 2.3a, that's the figure here. Okay, so he went for one run, right? And he went for a second run. Now, figure shows that in the reverse direction, the car covered the same distance. And from this data, determine the average velocity of for each run. Okay, what's going to be the average velocity? You know, delta x over delta t, right? All you have to do is to do the math. So here you go for each, right?
Professor,
Mhm.
I have a question.
Go ahead.
But it's not about the problem that you're talking about right now. I just log into my Wiley Plus, right?
Yeah.
My 13-day trial is over, but I cannot buy. The 14 days trial, but I can no longer buy the book anymore. I don't know why. I cannot buy it. What am I supposed to do?
Yeah. Well, did you try to call Wiley and ask them
I
about
think I
that?
did before,
Huh?
but should I call them again?
Yeah. I do not know why you cannot buy the book. Okay, but yeah, call them and find out. Did anybody else had this problem buying the book? I believe most of you managed to buy the book, right? Yeah, try to talk to Wiley Plus, give them a call and see what's going on. Okay. I really do not know why you cannot buy the book. It's their website should work properly. Okay.
Okay, thank you.
But yeah, keep me posted what's happening there. Okay. But I heard from other students that they were able to buy it. Okay. So let's go back to that. Okay. So 1609 meters, and this one right here, 16 109 meters. It's kind of straightforward, right? All you have to do is to do this math, and that's going to be 4.740 seconds. When you do the math, that's what we get. 339.4515 meters per second. That's what I'm getting here. And the arrows in the box at the top. And this one here was slightly less, right? 4695. Most likely that because this guy was moving with the wind. Most likely that because the wind was blowing from the right to the left, and he managed to do the same displacement. This not the same displacement, the same distance in a shorter amount of time. Okay, but because we have a negative value here, your velocity is going to be negative as well. Okay, so let's do that. 4695. And this one here, I'm gonna even do the following. Here go D, that's gonna be meters, right? I'm gonna put the problem. And by the way, I encourage you folks to learn Excel so you can do your problems as well, right? So here you go. D is 1609. Not D. Let's see. Delta X. Let's put delta X here. Delta X, and I'm gonna change the symbol right in here. One six oh nine meters. I'm gonna move this guy right in here. Delta T1. I want to put that like delta T1 because it was to the right. To the script. Okay, and then I'm gonna put this one was 4.740, not in meters but in seconds. 4.740. Right, and we have my speed one.
Professor, how do you make that delta sign?
The delta sign, let's see. Let me finish here. I'll show you how to do that.
Okay.
Okay. Okay, so here you go. Delta is capital D. Okay. So now you type capital D, you right click on capital D, and then you change the font to symbol. Okay. That's how you do it.
Wait, I'm sorry, D to symbol?
Yeah, the font, right?
Yeah.
Okay, there are all sorts of font in Excel, right?
Oh, yeah, now it
There.
works. Okay.
See that?
Yes,
And
now, yeah.
if you want to change to Greek letters, you have to use symbol. Like
okay.
those things you have to memorize. You have no choice here, okay? A,
Okay.
A in symbol for A is alpha, is the Greek letter alpha, right? You have to memorize it. There's no other way, okay?
Okay, thank you so much. Yeah, I just got it.
Okay. And then let's see, what I'm gonna do is I'm gonna put F. I'm not gonna put S1. I'm gonna put S. The other displacement is minus 1609, right? But then he went for a delta T that was shorter, 4.695. 4.695. Like I said, most likely it was slightly less than the other one because he was moving with the wind. The wind was propelling him. Okay, that's what we call downwind. There's downwind and there is upwind. When you're moving against the wind, we call upwind. When we're moving with the wind, we call downwind. Okay, so this equation that you have here, I'm going to do like that. This divided by this, right? and I don't need that. Here you go. Now I got this, I get the same one. And what about this one? Here you go. A little bit more, see that? The only difference is that we have a negative number here. It's a little bit more because he was moving downwind. 342,705. Let's make sure we got exactly what the book said, right? Okay, delta x here positive, delta x is negative. Okay, run on 339.5. Is that what I got? Yeah. Oh, he rounded up to 0.5. 1, 2, 3, 4. Yeah, it's right. And I'm gonna put in the right number of significant digits. We're gonna cover that in our lab. Okay, since we have 4 digits here and 4 digits here, this result should be 4 digits as well. Here we have 4 and 4. Also, this one has to be 4 digits, which equates to a single decimal place. Okay.
What's the equation again? How
Oh,
do you
it's
do that?
is delta x over delta t. That's the equation, right? Here you go. Take a look here. E2 delta x over delta t, which is F2 in Excel.
Okay.
Okay, and then Excel has this nice feature, right? That you don't need to repeat the forms. All you have to do to save you time, you click on the box and you drag to repeat the formula down below. I don't need the subscript one either. And I'm using the speed here. S for speed. If I want to make it look nicer, like, italicized, I can do that as well. Okay, speed, I'm gonna make my speed italicized to here. Right? So that's one example, simple example that is in the book. Okay, now we have the instantaneous velocity that I cover with you. Okay, and now we're going to start talking about acceleration. Okay, and by the way, let me write down here as well. It's not the speed, it's average speed. Average speed. Okay. Distance traveled. What is acceleration? Okay, so now we have called that average velocity. We don't, average velocity is what you saw before. Let's see. Average velocity is AVG. Delta x over delta t. Right? And then instantaneous velocity. We need the definition of instantaneous velocity to define average acceleration. All you have to do is to put that limiting condition that I put that for you. Here you go. Instantaneous velocity. Now, what we're going to define next is not called just acceleration, it's called average acceleration. And now we can copy and paste our progression here of definitions. Okay. We need the definition of position to define displacement and distance traveled. We need the definition of displacement to define average velocity, and we need the definition of distance traveled to define average speed. That's why I'm putting that in this progression, right? And then same thing applies to average acceleration. We need the definition of instantaneous velocity to define average acceleration. And by the same token that we have the definition of average acceleration, we also have the definition of instantaneous acceleration. Okay. Can go, see, primary, secondary, tertiary, quaternary, and so on. Right? How is average acceleration defined? Just go back the definition of average velocity. Okay. If average velocity is delta x over delta t, average acceleration is one step up. We replace the x with v, right? Is final instantaneous velocity minus initial instantaneous velocity. Like that. That's how we define acceleration. And if you want to define instantaneous acceleration, it's just like we did for the velocity, instantaneous acceleration. This parameter acceleration is a very important one, by the way. That's why we define it. Okay. It's a very important one. Can you remember that? Okay. So let me give you an example. Acceleration. Right here, final velocity minus initial velocity. Let's take a look at an example. Acceleration and increasing velocity. Here we have a jet plane. Initially at rest, right? Yeah, initially at rest. The plane accelerates down the runway and at t equal to 29 seconds attains a velocity of 260 kilometers per hour. That's very fast, right? That's compared to the Formula One car, where the plus sign indicates that the velocity points to the right, determine the average acceleration of the plane. Well, that's straightforward, right? All you have to do is to use some problems in physics are rather straightforward. It's just a straightforward application of mass of the definitions. But then there are some other problems that become a little bit more difficult because you require to use more than one formula. And by the way, here is average acceleration. Okay, here you go. This problem that we're doing here is sort of straightforward because it's straightforward. It's easy because it's straightforward application of definition. Okay, and you go 260, right? Let's take a look. 260 kilometers per hour. 260 kilometers per hour. And look, I'm going to put all the units in there. The initial velocity is 0. And the delta t is what? 29 seconds. 29 seconds. 260, right? The unit of acceleration, by the way, we can do a dimensional analysis here. Oh. Okay, it's going to be what? The unit of delta V divided by the unit of delta T. the unit of delta V is meters per second. The unit of delta T is the seconds. And so what you end up getting is meters per second square. Okay. Here we do not have meters per second square. We have, 260 divided by 29, right? Kilometers per second per hour, like that. That's what we have here. If I want to change that to the regular unit for acceleration in the SI system of unit, what do I have to do? I have to change kilo to 1,000, right? Kilometer to 1,000 meters, and I have to change hour to seconds, which is 3,600 seconds. Do you know that? How we get that? 1 hour has 60 minutes, right? 1 minute has 60 seconds. 60 times 60 is 3,600. Okay, and then you go. Those 2 zeros cancel out, right? One more here, and I'm gonna do that, and then seconds combined with the other second. This second here combined with the other second, and we are left with this calculation. 2,600 divided by 29 times 36. Okay, we can do that here in Excel. 260 times 10 divided by, going back here, 29, 36. 29 times 36. I'm getting 2.49 meters per second square. 2.49 meters per second square. Is that what the book says? He's getting a 9. Okay, didn't do the math. Okay, he put it in kilometers per hour per second. Let's see if he converts. Doesn't look like he converts. Let's see. 72. He's getting 2.5, huh? Let's see, what did I get? Yeah, I got 2.5 too. It's almost 2.5. I have to worry about significant digits. I'm not going to cover significant digits, but what he did here, he just rounded up from 2.49 to 2.5. Okay. So that's, we do have positive accelerations as well as negative accelerations. But the same token that we have positive, okay, acceleration and velocity can be either positive, 0, or negative, right? And that's what the next example in the book is all about. Acceleration and decreasing velocity. A drag racer crosses the finish line and the driver deploys a parachute and applies the brake to slow down. Okay? Here you go. Here's a drag car. Those cars are very fast, right? Deploys a parachute to slow it down. And he's asking what's going to be the acceleration. When t equal to 12 seconds, the velocity has been reduced to 13 meters per second. What's the average acceleration of the dragster? Okay, that's a very simple example too. It's just a straightforward applications of formulas. Okay, so let's do that together. Okay, I'm gonna use example. I'm gonna write that down here. Example 3, right? The other one was example 3 in the book. Example 3 in the book. This one here, example 4. Example 4 in the book. Okay, average is that 13 meters per second. Take a look. No, yeah, 13 meters per second. 13 meters per second. That's the final velocity. Initial velocity was 28 meters per second. And delta t was 12 seconds. 12 seconds. Oops, it's seconds here, not 2. That should be 15 here. Yeah. 15 meters per second, but let's not forget it's minus 15 meters per second. 12 seconds. Right? And now we have to divide 15 by 12. We can do again that in Excel. I'm going to use the same unit that we're going to end up using the same unit that we had before. I don't need that anymore. 15 divided by 12. 1.25. 1.25 meters per second square. Is that right? Let's take a look here. He got 5. Let's see. What did I do wrong here? Oh, there's more to it. Let's see. A drag racer crosses the finish line. The driver begins slowing down. Oh, it begins slowing down at t equal to 9 seconds. Okay. And the car velocity is okay. Okay, so he wants the average acceleration between 9 seconds and 12 seconds. Okay, that was my mistake. Okay, so let's do it. Let's do that again. It's not 12 minus 9, right? 12 seconds minus 9 seconds. 12 seconds minus 9 seconds. That's the right way of doing that. And then we have 3 seconds here. Now we get what the book gets. 5 meters per second square. Yeah. So sometimes you have to read the problem very carefully, okay? And drag racer, so let's read it again. Drag racer crosses the finish line, the driver deploys a parachute, apply the brakes to slow down. The driver begins slowing down whenever t equal to 9 seconds. Okay, from 0 to 9, he's accelerating. And then at 9 seconds, he deployed the parachute. Okay, and at this moment that he deployed the parachute, his velocity is 28 meters per second. At t equal to 12, the velocity reduced to 13 meters per second. That watch out, right, for those problems so you can solve it properly. And that's the direction of the acceleration. The velocity is to the right, the acceleration is to the left. The acceleration is decreasing this arrow, this velocity arrow, as time goes by. Here you go. At one instant of time is 28 meters per second, 23 meters per second. Notice that the arrow is decreasing. The length of the arrow indicates the number of the numeric value of the velocity. Okay. So keep that in mind. And acceleration is a very important concept in physics. We are going to look at that over and over again for different problems. Okay, and make sure you have this idea very well established in your head, okay? And it's not difficult to memorize, right? If you memorize the definition of velocity, okay, you can certainly memorize the definition of acceleration, right? I'm going to put them side by side. Here you go, average velocity. Average velocity. And then I'm not even gonna copy that. I'm just gonna copy this one here and change the symbols, right? And we do the same for instantaneous velocity and instantaneous acceleration. Yeah. Instantaneous velocity and instantaneous acceleration. Like that. XVA, right? Position, velocity, acceleration. That's how it goes. XVA. And now we can start thinking about constant velocity. 10:55. Let me go for another 5 minutes and then we take a break, okay? Constant velocity. Okay, this is a very important. This is a very important type of motion. We observe that frequently in real life. Okay, so think about that. I'm gonna ask you, what is the acceleration of a car that is moving with constant velocity? Constant velocity, right? And then I'm gonna make you another question. Do we have to know the numerical value of the velocity, right? Of the velocity of the car, of this car, to determine its acceleration, right? There's a question that I'm asking you. Think about that. Okay. Solution. 3 more minutes to go before we go. This is, what's the acceleration of a car that's moving with constant velocity? 10:57. Okay, the answer, for this, the answer for the second question is no, you do not have to know the numerical value of this velocity to find the acceleration. Why is that? You do not have to know because the final velocity, because it's constant velocity, okay? The final velocity is equal to the initial velocity. That's why. If the final velocity is equal to the initial velocity, so here you go. What's the average acceleration? Let's put it this way, right? Then the average acceleration, which is written as being Vf minus V naught, right? Can be rewritten as what? You just replace Gf with V naught here. Okay? And V naught minus V naught is going to be 0. 0 divided by delta t by a non-zero number is going to be 0. Okay? We find this type of velocity in many cases, okay? Examples, okay? Examples of constant velocity. Example of cases. Example of real life constant velocity. Constant velocity, okay? Puck moving on the top of a air hockey table. Right? You give a little push to the puck, do not touch it anymore, and until it hits the other side of the table, it's gonna move with constant velocity. Okay, you can also car, right? Car moving at 60 miles per hour in the freeway, in a straight stretch of the freeway, in a straight stretch of the freeway. There's another one. Okay. Another example that I like to tell my students, skydiver. After it jumps from the plane, sometime after right? She jumps from the plane and reach terminal velocity. Those are examples of constant velocity. There are more, okay, but let's stop here. It's 11 o'clock right now. Any questions?
I have a question about purchasing the book.
Yeah.
It seems like they don't know what to do. Like I was trying to follow their instruction and everything.
Uh-huh.
So basically, this person got me a link where I can purchase the book. So I clicked the single term and log into Yli Plus, right?
Yeah.
But it would just take me to the your assignment page where I need to where I read the book, where you use the book. But I don't have books right now, so it would just there's only expired books remaining and
Really?
from the website.
Well, we can
And
let's do that during my office hours. Okay, stay around
okay.
during the office hour. I'll call and let's see what's going on, right? I want to know from the other students, are you having the same problem that Camden, right? Is having
Yeah.
anybody else is having the same problem? Let's see.
And
Uh-huh.
I have one more thing to tell you. So when I click the upgrade now, you
Uh-huh.
would just give me this error message it's taking longer than usual to process your new Walleye Plus account, which is required to move forward to the cart. Please wait a few minutes and then try adding to cart again, blah blah blah. This happened like 14 days ago, 2 weeks ago. That's why I had to use the free trial version first. But I don't know why I'm getting this message again.
Yeah.
And
Yeah, we need to do that during the office hours. Okay, let's. I need to see
okay.
what you see in the screen. Okay, what you're seeing on your screen right now. Let's wait until the office hours, and you're gonna share the screen with me. Okay, and I'm gonna try to figure out what's going on with you. Okay, and hopefully we get someone from the from Miley Plus to help us out too. Okay, let's do it this way.
Okay.
Okay, and I want to know from the other students. Let's see, Ashley, are you having the same problem, Ashley? Ashley and Abel, right? No? Okay, Ashley, so you managed to purchase. Mine is working fine, but I bought the single semester and did not get the free trial. Okay, you went straight to the okay. Annabelle didn't have any problems. Vanessa said that she didn't have the free trial, right? Right, Vanessa, you went straight to purchase. Okay, and Destiny, what about you, Destiny? Do you have any problems?
No, I don't.
No. Okay. Eric Martinez, do you have any problems as well? Looks like Eric's not here. But in your case, must be something in your computer, okay? But we will figure out. It looks
Okay.
like, yeah, it looks like it's something there that in your computer, and Miley should be able to help us
Okay.
on that. Okay.
Yeah. Thank you, Professor.
Okay, yeah, Norberto also I had no problems. Okay, that's good. That's good to know, Norberto. Thank you. Okay, it's 11:05 right now. So let's go for break 11:05 to 11:20 a.m., right? I see you in 15 minutes. Yeah. Okay, I'm back here. Okay, so now we defined everything that we want to define to start analyzing the motion. Okay, we defined everything that we needed to define, to start to start our real study of motion. Okay, so let's go back to the types of motions that we have out there. Let's see what I put down. Here you go. Okay. Here are the types of motion that we have. And what we defined position, right? We defined, I'll put here as a list. One, position, displacement, average and instantaneous velocity, and average and instantaneous acceleration. Okay. And then we're going to start studying with these definitions. We will now start studying the types of motion. Okay? We have, four, maybe even more. Okay, you can define all sorts of motion, but the most important of them for now are those two: uniform motion, which is constant velocity. Okay, constant velocity. So let's start. With a special case, constant velocity. Constant velocity is the simplest type of motion you will ever see. Okay. So what's our goal? Our goal for all types of motion is to obtain the equations of motion. And what do I call the equations of motion? Okay. Equation of motion is the following. Oops. Equations of motion. I'm going to put it in capital letters. Equations of motion. Equations of motion is how the position changes with time. That's one of the possible equations of motion. There are three equations of motion. The other one is going to be how the velocity changes with time. And finally, how the acceleration change, if it does, how does it change with time? That's what the equations of motion is all about. The equations of motion are relations of x, v, and a of the position, velocity, and acceleration in terms of time. That's what the final goal of the study of kinematics is all about. To find the x, v, and a in terms of time. Okay. For uniform motion, we already know, right? That we already know that the velocity does not change as a function of time, In other words, the velocity alone is constant for this special case, which implies, because the velocity is constant, this already implies, and I mentioned that before, that the acceleration is 0. Out of the bat, I already have 2 of the equations of motion here. Okay? Out of the bat, I already have 2 of the equations of motion. Just by defining the type of motion as being uniform motion, which is constant velocity, I already know what's going to be, how the velocity is going to behave and how the acceleration is going to behave. Now, we are left, okay, with calculating the position. Okay. In order to calculate the position, okay, we need to calculate the position, right? To calculate, make it simpler here. Calculate position. All we need is to go back to the definition of average velocity, or going back to the definition of average velocity right here. Okay. Now, because velocity is constant, we can here write the above as, okay. Right? Because the velocity is constant, the average velocity is going to be equal to the velocity itself. Okay, which is going to be equal to delta x over delta t, which, by the way, I'm going to spell that out even more, xf minus x naught and here is delta t, can be here written down as tf minus t naught. Do you understand how I make this equality here? That's straightforward, right? Velocity doesn't change. So since velocity doesn't change, the average velocity is going to coincide with the instantaneous velocity v. And what we're going to do here? Okay, we can choose the initial instant of time as being 0, which will simplify our equation. Or okay, I don't need the average here anymore. I don't need this guy here anymore. And then, T naught disappear. We'll do another simplification. We'll do another simplification. We will rename XF and we'll call it as X, or XF is going to be, we do that just to simplify our notation, okay? So keep on carrying There's no need to keep on carrying our F subscript everywhere. And we do the same. We'll do the same to T as well. We will. And we'll do the same for TF. We'll do the same for TF. We're gonna drop the subscript. You know, consider X and T as though they are just a nickname for the variables. Okay. When you do that,
Professor,
yeah,
I have a question. Is this chapter 1?
this is chapter. It's chapter 2, right? Let's take a look here.
Chapter 2?
Yeah, I believe it's chapter 2.
Chapter 2.1?
Let me go there. Well, no, I don't have it by heart exactly which section that is, but let's go to the book. Here you go. That's the one. Equations of kinematics for constant acceleration. Doesn't look like they have for constant velocity. It's not in the book apparently. Okay, they just jump into the more complicated one. Equation of kinematics for constant acceleration. It's not. They don't have for constant velocity. Which is a shame. You know, they should have done that for constant velocity as well. Yeah.
Oh, okay.
Yeah, they didn't. Yeah, they didn't do
I
for constant
purchased the
velocity.
book, so I just wanted to make sure if it was
You
there.
purchased the book, you said?
Yeah, manually I
managed.
did.
You managed
Yeah.
to purchase the book? Did you
Yeah.
find out what was the problem?
They don't know, but I had to call them and I provide them my personal debit card information. Yeah, and
okay.
got the code. Yeah.
Okay, that's good. Okay, so problem solved, right?
Yes.
Okay, congratulations. Okay, I'm happy. But they don't have the equations of kinematic for constant velocity. It's odd, you know. Why they don't have it? It's really odd. Yeah, all the books do have that. Okay, but it's somewhere between 2.3 and 2.4. Okay, we're gonna cover 2.4 hopefully before the end of today's class. Okay, so here you go. Now let's apply the simplification. We cannot drop the not here. We cannot, because if you drop the not, you're going to, you know, think about that. If I drop the not here, you're going to subtract one thing that's one x, the final x with the initial x, right? You cannot do that. That's why you don't drop the not. You can drop the f, but not the not. Okay, that's the, and then remember, what are we doing? We found these two equations of motion, right? And now we have to find this one. Let's see how it looks like. Let's see how it looks like. Okay, we are almost there. See, we want to find this guy. I'm going to boldface it. I'm going to boldface it so you know what we're trying to do. So the first step is to multiply both sides by t, right? And then solve for x. Okay, so we end up getting x naught plus vt. So those, we finally have all equations of motion for constant velocity. Okay, the equations of motion for constant velocity, the equations of motion for consequently, the equations of motion for constant velocity are this one, v constant, and because v is constant, the acceleration is 0. Okay, Those are the equations of motion for constant velocity, for uniform motion. Constant velocity, constant, or uniform motion, or simple enough. Is a linear, x position is a linear with t. Okay. Let's analyze it. Let's see. Okay, let's see if I have a slide for that. Okay, here you go. Here we have a case of x versus t, right? And you can see that clearly that this curve is not representing uniform motion because it's not a straight line, right? If you were to represent a straight line, let's see if I have it here. I don't have it. What a shame. Let's see. That's vectors. Huh. I have to do that from scratch. Okay. Let's do that from scratch and oh, that's what I want. Yeah. Okay, this one. Can do better than that. Yeah, that. Right here. Oh gosh. Yeah. Okay, here you go. X and Y. X. Okay, so don't forget to put the units. Yeah, units are supposed to be there all the time. Should be lowercase f, x. Right, we go. No, x goes here, right? You go. What goes in the horizontal is t. And that should be seconds. So how does that equation looks like in an x versus t graph? It looks like just like a straight line. Like that. Okay, constant slope. Do you see it's constant slope? Constant slope means constant velocity. What you have here at this point crossing the x-axis, the position axis, right? Let's call it the position axis, is the initial velocity, initial position, like that. This point here is the initial position, which corresponds to t equal to 0. Everywhere along this line, the velocity is constant. The slope here is the same as the slope here, the same as the slope here, the same as the slope here, because this is a linear graph. That's how you should interpret. The steeper this slope, the faster the particle moves. Okay, the steeper the slope, the faster the particle moves. Let me get a little notch here. Here you go. Oops. And I'm gonna make it a little bit thicker. Okay. Notice that I put the units, meters and seconds. That's how it looks like. The graph can be like that. You know, all sorts of different graphs. Okay. The graph can be like that. Okay. The graph can be two other ways as well. The graph can be like that. Those are all the possible graphs that you're going to see out there for constant velocity. And I'm going to do even better. Here you go. Move upwards. And the other one that you'll be able to see is going to be like that. Okay. Let's take a look at the four possible ways that you can have. Positive slope, positive intercept. X naught is the intercept. Positive slope, negative intercept. Negative slope, positive intercept. Negative slope, negative intercept. Okay? The slope represents the velocity. The intercept represents the initial position. So negative velocity, negative intercept. Negative velocity, positive initial position, right? X naught. Positive velocity, negative initial position. Positive velocity, positive initial position. Four different types of graph that you're going to see for this type of motion. Okay. 11:45. What else can we have here? Let's do an example. Let's see, example. Example. Let me copy and paste something here. Okay, instead of doing an example, here I'm going to show you, there are the simplest problems that we have that you're going to see for this type of motion are the following. Okay. Given initial position, V and T, find X. Okay. I'm going to do like that too, instead of A, B, C. Given X, V, and T, find X naught, right? Given X naught, X and T, find V. And given X naught, V and X, find T. That's the simplest type of problem that you're going to see for this type of equation. But there are problems that are more difficult. Then you have problems that are more difficult, okay? And that's where the example comes into play. Okay, here you go. Here you go. Given two cars in uniform motion, car 1 and 2, they are moving the same direction with non-initial positions, x naught 1 and x naught 2, and non-velocities v1 and v2. Okay? Let car 1 be ahead of car 2, but moving with a velocity that's lower than the velocity of the other car. The speed of 1 is less than the speed of 2. So find 1, the instant of time that car 2 catches up. Car 2 catches up with car 1. The position that car 2 catches up with car 1. Okay? So that's a more complicated problem. That's a more complicated problem because now you do not have just 1, 2, 3, 4. You have more. Okay? Let's see what we have. Let's see. In this case, it's somewhat related to this one, but instead of x naught, we're going to have x naught 1, x naught 2. We're going to have v1 and v2. And v2. v1 and v2, right? Find, what do we want to find? Find t and x. And x. That's what we want to do. Item 1 is find t, right? Find, let's put it this way. Item 1, t. And item 2, x. See how much more difficult this problem is. Here we have just a single equation, but here we're going to end up having two equations, and we have to find two parameters. And there is a proper mathematical procedure for that. We have 10 more minutes to do it. Let's do it together. Okay, what you have to do, you have to come up with the equations of motion for car 1 and car 2. Here you go. Okay, so instead of a single equation like you had here before, now we have two equations.
Professor, so
Yeah.
x1 is the car 1
That's
and
right.
okay.
It's the position of car 2. Position of car 1, position of car 2. Okay?
Okay.
And then the instant of time that car 2 catches up with car 1. Okay? At the moment that car 2 catches up with car 1, what's the condition, right? What's the mathematical condition? Here you go. The mathematical condition for car 1 to catch up with car 2 is, what's going to be the mathematical condition? The mathematical condition is that the position of car 2 is going to be equal to the position of car 1, or vice versa. Okay? Given, let's say, instant of time that car 2, yeah. And you want to find t. Find t, right? Given, here you go, item 1. Item 1, find t. Item 2, find, it's not x, that should be x1 and x2, right?
Professor, I'm
Yeah.
so sorry. But
Yeah.
how do I read the v velocity not one time? I don't know how to read that.
Where are you reading?
The equation, the x1 equals
naught.
x1 not and plus, and how do I read the other one? The last
V1t.
v1t. Oh, okay.
V1t, yeah.
So that's
V1 is
velocity one
velocity.
and time. Okay.
Velocity of car 1, velocity of car 2, right?
Okay.
And it's written here as well. Initial position of car 1, initial position of car 2, initial position of car 2. 11:52, we have eight more minutes to go, right? So here we go, we're going to apply the condition and car 2 catches up with car 1. And all you have to do is to combine those two equations, right? Here we go. And I'm going to do like that here. X1 is equal to X2, here we go. I'm going to get X2, that's here. I'm going to paste it here. I'm going to get X1 here, and I'm going to paste it here. And notice that I want to know T, right? T and T. That's what I want to know. I eliminate X1 and X2.
But I have a question.
Yeah.
But I thought the car 2 would pass the car 1 eventually.
That's right.
So how is that? It's even like between those two.
Well, let me illustrate that for you. Car 2 is behind, right? Given two cars in
Right.
uniform motion, car 1 going in the same direction with non-initial positions. Here you go. X2, and I'm going to do something else too, okay? And non-velocity, I'm going to do something else here. X0, X01 is greater than X02. I didn't do that, right? But I did the other. And non-velocities, V2 greater than V1, right? Let car 1 be ahead of car 2, but moving with V1 less than V2. Okay, so the situation is like that. I'm going to illustrate here for you. Play the movie, right? I like tell my students that you have to play the movie in your head. Just like Tom Cruise does in his Mission Impossible movies, right? Have you seen him? Have you watched Mission Impossible? They show that in more than one Mission Impossible movie, he plays the situation in his head. He's predicting what's going to happen, right? That is really nice the way they did it. It's really someone that is doing the movie is playing the movie in his head. That's what Tom Cruise does in at least 2 of the Mission Impossible movies. Maybe he does in the others as well. Let's see, size and position right in here. So where I'm gonna do that? Okay, I'm gonna get rid of that. Okay, the situation is like that. Okay, at time t equal to 0, here's the freeway. Okay, at time t equal to 0, car 1 is here, right? And car 2 is here. Make sense?
The first one is the X1, right?
Yeah, this one is X not 1.
Yeah.
That's right.
X1.
Let me label it, this one here. But don't forget, it's the second car that's moving faster, right? So eventually, right? That's initial position X01 and X02. So I'm even gonna label this one car 2 and car 1. So it's very clear, right? Car 2 and car 1. And I'm going also to depict the velocity of car 1 and 2 with an arrow. And by the way, the arrow of car 2 is going to be longer then the arrow of car 1. Here you go, I'm going to like that. Car 2. And here is going to be velocity V2. Okay. Here you go. And you do the same for car 1. That's the illustration we usually do, so students can understand better in a graphical way. It's easier to understand the drawing than to understand words, right? And here you go, the velocity of 1 is shorter, right?
Yes.
Okay. A little bit later, what's going to happen? A little bit later, I'm gonna call that T1. $11.57. Car 2 has moved a little bit further down, right? And car 1 has moved further down, but not as much. And it's no longer X02, now it's X2. And now it's no longer X01, now it's X1, right? That's T equal to T1. Eventually, car 2 is gonna catch up with car 1. And I'm gonna displace it a little bit down, right? So you can see that, here you go. That's the instant of time that that's not good. I'm gonna put this one here. Here you go. Here better, right? That's the instant of time that I want to find out. That's T2. Oh, this should be T. Go X2. X2 coincides with X1. And by the way, they should be a little bit further down the x-axis. Make sense?
Yes, but if we apply the actual numbers, then do we need to have like 3 different equations to prove this, or?
Well, when you apply an actual number, you're going to do exactly the way I'm doing here, right?
Mm-hmm.
You're going to do exactly the way I'm doing here. Okay, let us finish that, right? Let's finish that. Here you go. X2 is equal to X1, right? So think as though as you have 2 meters here. Think as though as you have 10 meters here. Think as though as you have 10 meters per second here. Think as though as you have 5 meters per second here. Okay? That's how you should think. And then here you go. Don't forget V2 is greater than V1. So I want V1 on the left side with a negative sign. And I want X02 on the right side with the negative sign as well. Like that. Okay. And finally, doing, numerically is the same as doing symbolically. The only difference is that the symbolic notation is far more powerful than the specific numeric notation. Okay, might be a little bit difficult for you to understand, but here you go. That's how we solve the first problem, 12 noon, right? Here you go.
Okay, but that's the at the end, like when the car 2 catches up the car 1.
Yeah. What do you want to know?
I mean, that's what I wanted to know, if that's the final equation or not.
The final position? Are you talking about the final position?
Yeah, final position.
Okay, so here you go. Now all you gotta do, that's item 1, right? Item 1. Item A. It's not item 1, it's item A. What about item B? Okay, now you found out what's the instant of time that car 2 catches up with car 1. All you have to do is to get the equation for X2 or X1, either way, okay? Doesn't matter and substitute T right in here. All you have to do is that. Okay, so here we go. Right here, right? And then let's see if we can simplify that further. Let's see if we can simplify that further. Here you go. I'm gonna copy and paste here, but let's not forget that I have to copy this one up, right there. I'm reducing to the same denominator, right? And let's see, it's gonna be x naught, it's gonna multiply this guy, is not 2, right? This one, okay, v2 is going to multiply this one, and it's going to multiply this one. Let's see, can we, oh, these two, they cancel out, see that? These two, they cancel out. And, okay, this one here, oops, same denominator, right? They cancel out. Because one is negative, the other is positive. Those two cancels out. And then we are left with this term here. Can we simplify? No, we cannot simplify more. So that's the position that they are going to be whenever one car catches up with the other one. Just then a little bit later, car 2 is going to be ahead of car 1, right? If you're going to, illustrate it, if you want to illustrate a little bit later on. Let's see here. And then T3, right? T3, car 2 is going to be ahead of car 1. Like that. Okay?
Yes.
And I can erase that. So it's 12:04 now. We can stop right now. And do you have any questions? Don't forget I have an office hours now.
Are you going to upload the lecture video right now?
Yeah.
Okay. Where do I find the lecture video?
Well, in the Canvas,
Canvas?
site. You go. Canvas right here. You go the lecture home. Okay, student view, right? You view something like that. That's what you see, right? Syllabus, right? Okay, and then I put the links to the video. The notes are here. Fall 2023.
But the first video is not working because it's private or something like that.
Really? Let's see. Let's play it. That's the first video here. It's supposed to play. No.
Yeah, mine is like this video is private. I think it's not public.
It looks like you have. Yeah, it looks like you have a problem there in your computer, right? Yeah. I do not know it's private. I don't know. Maybe it's your. Yeah.
And the second video is not working neither.
Neither?
Is that,
Let's see.
no.
Let's see.
So
Here you go. See, it's working.
I can share my screen and show it to you.
And yeah. I'm gonna put also as a group assignment, right? Okay, so let's see. So there might be something there in your computer, I do not know. Maybe there's some protections that. What are you using? Are you using a Mac? Are you using a PC? What are you using?
Oh, I am using PC, but
PC?
one of the students just mentioned that I need to directly open the web browser to play the video. But let me try.
No, I don't need it. I don't think you need to open your web browser. But let me see. Let me share the screen with me. Let me stop sharing my screen.
The second one is working. If I